In this video, we're going to start off our quadratic function unit by taking a look at the different characteristics of a quadratic equation and how we can use those characteristics to create a graph of the quadratic function. So first, we want to just real quick recover what a quadratic function is. So in our polynomials unit, we learned that any polynomial with a degree of 2 is a quadratic function. So that's what we're going to be focusing on here, just quadratic functions with the variables x and y. And we're going to look mostly at them written in standard form. So we have ax squared plus bx plus c. A is always going to be the coefficient of the squared term, b is always the coefficient of the linear term, and c is always going to be our constant. And when we graph these quadratics, the graph that we get is called a parabola. That parabola is a U-shaped curve that either opens upwards or downwards. The opening of that depends on the value of a, that coefficient of the squared term. If a is positive, our graph is going to look like the smile, a very happy positive person opening upwards. And if a is negative, our graph is going to be the frown, like a negative person. The point at the top or the bottom of the parabola is called the vertex. So same word that we use for corners of shapes or angles in geometry. When the parabola opens up, that vertex has the minimum value, the lowest y value for the function. When it opens down, the vertex is the highest y value we could get, or the maximum. The axis of symmetry is a line that divides my parabola in half into two equal parts. And if I have a point on the left side of the axis of symmetry, it matches up with a point with the same y value on the right side of the axis of symmetry. And we're going to use that to help us graph. So when we want to go to graph these, the first thing that we need to do is identify those values of a, b, and c. So in this particular quadratic, a is -1, b is 8, and c is -12. And I'm always going to start by finding my axis of symmetry. The axis of symmetry is defined as x equals -b over 2a. This is a formula that you'll have to memorize. We won't give this to you. And then we're just going to plug our values in here. So we have -8 over 2 times -1, which is -8 over -2, or 4. And because the axis of symmetry is a line, we're always going to write it as an equation. That equation is always going to start with x equals, because it's a vertical line, and in this case it's x equals 4. When we put it on our graph, we do it as a dotted line because it's not actually part of this function. It's more of a reference point for us. Once we've got our axis of symmetry on the graph, we have a general idea of where the quadratic is going to be located. We know it's got to be somewhere along this line, which means that it has an x-coordinate of 4. So my vertex is going to be at the point 4 something. This means I'm going to take my 4 and substitute it in for x into my function and figure out what the corresponding y value is. So we're going to go ahead and evaluate this function for 4. And we'll solve. So we have -16 plus 32 minus 12, which is going to give us a y coordinate of 4. So my vertex is going to sit at the point 4, 4. Once we've got the vertex, we're going to use our graphing calculator to find other points that we can plot. So I'm going to go to my calculator, and I'm going to go to y equals, and I'm going to type in the equation that we're given. So we have -x squared plus 8x minus 12. If I look at it, I know that my lead coefficient is negative, so it's going to be facing down. We've got our axis of symmetry on the right side of the graph, so if I hit graph, I can get just a quick look. Everything seems to be correct. And now I'm going to go to the table. So in the table, we can see all of these ordered pairs that make up the function. And I want to pick ordered pairs that are going to fit in my graph. So if we start, we have 1, -5. So I'm going to come back to my graph. We're going to go over 1 and then down 5. I'm going to have a point there. And now remember, we can use our symmetry. So this point is 3 units to the left of the axis of symmetry, so I also have a point that's 3 units to the right of the axis of symmetry. I'm going to look for another one. We have the point 2, 0. So we come over 2, and we've got this point here. That's 2 units to the left. We also have one that's 2 units to the right. Then I look, and nothing else is really going to fit, so that's as good as we're going to get. When we graph quadratics, we want to usually get at least 5 points. So it would be our vertex, and then 2 pairs of symmetrical points. So we can go ahead, we can connect the dots. We want to do our best to show the curved shape of the graph. Okay, and we always put arrows on the end just to show that that graph continues. The last thing that we're going to do is identify our domain and range. So for my domain, as this graph continues on, it's going to get wider and wider and wider. So I'm going to hit every single x value along the way. So my domain is going to be all real numbers. This is what it would look like in step builder, and this is what it would look like in interval notation. My range depends on my vertex. So here my vertex is a maximum, which means that all of my other y values are going to be less than or equal to that. So for my range, we want all the values of y that are less than or equal to 4. And then in interval notation, that would be everything from negative infinity up until 4. So go ahead and pause the video, try to graph this function, and see if you can identify the domain and range. Alright, so for this one, we got our a, b, and c. We can identify our axes of symmetry using our formula. We get x equals -1. Then we substitute that in to find our y coordinate of our vertex. Then we use our calculator to find the remaining points on the graph. Our domain again is the all real numbers. Our range this time is everything greater than or equal to -3. One thing I do want to point out here is that there's one more piece of information we can pull from our equation. If you look at our graph, our y-intercept here is at -1, and the constant in this function is at -1. Remember that our y-intercept is the point where our x-coordinate is 0, so if I substitute 0 in for x, this term will cancel out to 0, as will this one. So whatever our constant is in standard form is going to be our y-intercept.